In neuroscience, there's a thing called default mode network. That's what brain does when it has nothing to do. Well, ever since I was a child, my default mode network was mostly preoccupied on how something works, how can I fix something, or how can I build something. Each time I enter my shop, somehow I honor my creative child. After I finish my daily white-collar job, when I put this apron on, I enter into my true self, blue-collar inner child, who can't wait to try some new ideas or build something new. These two chucks laying on my bench were two nice additions for my leg work holding capabilities. But ever since I saw a video from We Can Do That Better, I decided that I want a collet chuck. This is the perfect opportunity to do some work that I can call like factory made. This lever-operated collet chuck uses 173E type collets ranging from 3 to 42 mm. These usually come in increments of 0.5 mm, but for the beginning I got about 17 collets with the most usual sizes. 2 weeks have passed since I received the package until I had the time to record something. So my curiosity has already killed the unboxing and cleaning shots. I am now exploding it so that you have an idea on what's inside. The chuck came with this threaded cone mount that I don't need, so if among my viewers I have someone with this spindle mount, I am donating it. You pay the shipping and it's yours. With this camlock spindle nose I can swap between my chucks in less than 30 seconds. So in order to mount this we'll need a camlock D4 backplate. A dual contact camlock backplate is not something quite trivial to build, but fortunately I have one sitting in a drawer for almost 2 years now. And the good news is that I have enough meat that I can get rid of the already existing holes. So let me grab a tool and prepare to make some chips. As you may notice, the way cover that I've built in a previous video is now limiting my Z- travel. It's doing a great job in keeping the dirt off my lathe bed, but for this operation I need to take it off. It's been a year already since I'm using it, and the video where I documented this was one of my most popular ones, so go check it out if you wanna know how it's made. Now I'm confident that I can go with the other retraction solution, so expect a video on that. When I mounted the way cover, I limited the Z- of the machine from the configuration file, so we need to revert that in order to have the entire Z-axis travel. Just a quick restart and we can reach the back of the flange. I'll use the quick cycles I implemented, but first we need to do a touch off and then set Z0. The initial Weiler controller had a nice way of entering the data, where you could position the tooltip wherever you want and then click Teach In. I like that feature, so I added it into my custom controller. For the X-end, I will just touch that input and enter the target diameter from the on-screen numpad. For the depth of cut, I have a list of predefined values that I can pick off. Clicking the load button will internally call a subroutine with these parameters that will use the current DRO values as start values, and it will do multiple passes with the specified depth of cut until it reaches the target dimensions. I know I said it in the previous videos, but I really love this combination between a manual and a CNC lathe. For the prototyping work that I do, I have the best of both worlds. With the OD turning complete, I now need the facing for the centering shoulder. The facing quick cycle allows me to lay back and admire the flying chips. And yes, I know I said this before, but the time spent coding into the ability of making chamfers using the joystick was worth it. Time to test the fit. And yes, with a shoulder of just 4mm I can barely pull it out when it's a bit crooked. Before we move it to the mill and make the threaded mounting holes, I need to remove the cam pins and knock off the burrs with a file. Time to start the mill work. I really like this wedge type vise. With the current jaws mounted, I can clamp a part that's 210mm long, and if I remove these hard jaws I get another 20mm. Basically, the entire wide travel of the machine is covered. Compared to my old vise, I really like that for this one I can change the jaws. The best part to hold the round part on the mill is a lathe chuck, so these custom made jaws are meant to hold the 6-inch 3-jaw chuck. Just some copper shims to not leave any dents and some hammer blows to sit it properly and we're ready. Before I do any machining, the controller needs to know where my part is located on the table. This touch probe along with the appropriate probing routine will set the XY0 at the center of my part. A quick fusion program posted into the drawbox of the machine handles the drill spotting and drilling for an M6 tap. This machine knows how to do rigid taping, but with a spindle of just 1.5 kilowatts, and without some proper tap collets, I don't want to risk ruining this part by breaking a tap into it, so I'll start the thread on the machine and finish them manually. With the backplate machining complete, off camera I bolted the screws and now I can continue changing it until it looks like it was built for my machine. The lever, it's way too long and it clashes with the sliding door of the machine, so even though I would need more force to operate it, I need to cut it shorter. This is a bit tapered and I don't like this old chipped paint, so I think I'm gonna take a few skin passes, hoping to get a nicer surface finish. I can't call this complete without a plastic end cap, so let's make room for that. With this M8 black cap mounted, I think it kinda looks like factory made. Did you thought I could finish this project this early without any over-engineering? Nah, that would not be me. I want a fast way of mounting and unmounting the collet chuck, and this is what I have in mind. Later, you'll see where this gets mounted. To build this mechanism, I have this chunk of chrome moly and this C45 bar. I got this chunk from a friend and I was very lucky to get it very close to its final dimensions, so let's start with this one. I'll start with the larger parts first so that I can hold on a clean surface when I flip it. With a combination between the manual functionality and a few clicks on the Quick Cycles UI, I've cleaned this side. And of course, let's not forget about some joystick chamfering. Now I like it. With the part being flipped, before I run the roughing cycle, I'll do a manually facing operation to have a clean reference, then set the Z0 for my part. To machine this side, I use a quick cycle for turning. The code for my custom controller is still work in progress, so I'm trying to navigate among some known bugs. Behind the scenes, the data that I easily enter here, it's used to create an ANSI program that gets open when I click the load button. Then, when I start the spindle, the machine will start executing that program. After all the time I've spent for rebuilding this machine and coding its software, I can't explain the satisfaction feelings that I get when I see it doing its job. But from time to time, a hot chip wakes me up from daydreaming. Just some quick chamfers and we're done. Time to do some cleanup. These blue chips are everywhere. I can't make one more step without these chips getting embedded into my soul. The way covers that I've made have done a great job in keeping the important surfaces clean of chips. If you wanna see how I made this, go check that video. Now I can finally unclamp this part. I was hoping for a nicer finish, but it doesn't look that bad. When complete, this piece will get mounted as a replacement for this cap. It will be useful just for the collet chuck, and from a length perspective, it won't interfere with the other chucks that I have. But before we replace the white painted cap, let's put some holes into this new piece. I already had the chuck mounted from the previous operation, but I needed some parallels to raise it just enough that I have the maximum gripping contact. And of course, the copper shims, to keep it free from dents. After I probe the height of the stock, each tool length is measured so that Z0 is correct for every tool that I need. This 8mm end mill was the only one I had with 30mm flute length. It's a bit too thin, but in order to avoid chatter I went with multiple smaller depths. Ideally, for the part finish and tool life I would be using flat coolant, especially on this kind of pockets where the chips are very hard to evacuate. But without an enclosure, I would be taking an unwanted shower each time I machine something. But I'm getting along quite well with this mist buster and some extra compressed air. Let's not forget about the chamfers. This time I've learned my lesson with the walking drill tips, so I decided to spot drill the holes before I do the M6 pass-through holes. For the countersink holes, I'm just plunging with an M10 end mill so that I get a flat bottom. So far I like how it came out. Let's replace the old cap with something more useful. The holes have lined perfectly and I have no interference with the chuck cover, just like I wanted. So let's continue by figuring out the appropriate length of the rod that will act as a support for the collet chuck lever. From this 25mm thick stock of C45, I need a length of about 130mm. So let's cut the chunk of it the default Tony way. I can't state how much I like that I ended up having both a lathe and a mill that I can use to build more accessories and more tools for the lathe or for the mill. Let's see how close we are. At 12:04, at least I still have some material to remove. How about the base part? 12:03. The internal jaws of the caliper are not the most accurate way of measuring, but I'm trying to fight my impulse of keeping tolerances too tight. Nah, it's close, but it's more like a press fit, and for a normal use I need a slide fit. I think another finish pass with a -10 micron stock to leave should do the trick. And this time we have a slide fit. I don't quite like this side play, but the vacuum sound that it makes has convinced me not to redo this part. Now let's take this off so that we can figure how to machine the other end. But first, let me enjoy a few moments of satisfaction. I can't let this sharp edge ruin my moment, so let's punish it. With the base bolted on and the chuck mounted, I can finally determine the correct rod length. This ensures that the collet chuck lever ends up in the correct position when closed. Before I machine the other end, I need to figure out the exact dimension. The old one is way too sloppy for what I want. The internal jaws of the caliper are not the best way of measuring, but I have something better. From an old communist factory, this set of gauge blocks has found its new home in my shop. After trying a few combinations of gauge blocks, It seems that this should be the size I should be aiming. The gauge blocks are sliding in without any play. Now is the right time to make my homemade fourth axis to be a part of a video. I want to have that boss centered exactly at the middle of the stock and have the same exact angle as the other one. And the center vise is exactly the right tool for that. But with a stick out like this, I could not do it without a tailstock support. So, time to take the vise off. Since I'm clamping this on a center vise and not on a concentric chuck, I need to indicate it to make sure it's aligned on Y and Z axis of the machine. Why did I use the vise instead of a chuck? You'll see in a few moments. By using the center vise, I can sweep the indicator on top of the vise jaw and slightly rotate the A-axis until it's parallel with the table. Then I can set that angle as being A0. After taking an X0, I can finally make some chips. I think I was a bit too greedy with the depth of first pass for my milling cutter, so I decided to go just 1mm deeper pass. Usually, I post the code from Fusion, but here I wanted to give myself a challenge and write the code manually with variables and while loops. It took a few hours to play with the syntax and do some tests, but I consider that as learning. And the satisfaction of seeing it work as I intended, priceless. I managed to get within less than 10 microns close to the target dimension, so it's time to test the matching with the mating part. It's exactly what I intended. Slide fit, no play at all. Now I just need a hole for the pin that comes in. So an undersized drill and a reamer, and the pin slides perfectly with no side play. But after I mounted it, I realized that I need a bit more range of motion on the left side. I could have done this right in the rod I've just milled, but now it's unclamped and I don't want to put it back on the fourth axis and re-indicate everything just for this. So I decided to go with some weird setups to remove some materials from this hinge of this ring. And now, with this clearance, we're free of collision on the entire range of clamped-unclamped positions. So far everything looks good, but I need a way to lock that back bar into its base. The locking mechanism that I have in mind is the same as for the camlock of the chuck. But for that, we need to make the hole for that cam into the base block. But for that hole to be positioned where it should be, I need to tell the machine the origins of the part. For the x-axis, I'm using a 10mm gauge block to touch on, then I will subtract this value to get the real 0. Oh, I envy you all American guys who have access to products like Anchor Lube. In the meantime, I need to use this smoky lubricant. For finishing the hole, a 15mm reamer would be ideal, but since I don't have one, a boring tool path will do the job. Just a small chamfer and we can go further. We're done with this clamping, so before I continue with the next part, let's clean it up a bit. The rod from which I'm gonna make the cam pin slides in quite easily. At this moment I'm pleased that I managed to get such a good fit, but this will bite my ass soon. The next step is to mill into the back rod the recess that will allow the cam pin to go in. Back to the mill. A good way of holding this part so that I have easily access with both the end mill and with the mating part, it's a pair of V-blocks. Now, in order to get the cutout in the correct orientation, I need to make sure that the flat plane is parallel with the table. For taking the origins, I can't say I had the best idea for the precision I was trying to achieve. I went more by habit than by thinking. I've messed something up and this is the result of those origins. Luckily, I still have material that I can remove. Believe it or not, it hit me just now that I could have used this hole to take the origin of the board that I'm milling. I've got a new chance. Better not mess it up this time. Now that's a totally different story. The base block needs two holes in the back. One will keep the cam in place and the other one will hold a spring and a ball bearing that will give me a nice detent. I went with two diameter drills, one is 4.2mm just right for tapping an M5 thread, and the other one is a 3.9 so that the ball doesn't wiggle. But on the smaller diameter deeper hole, in cam, I made a terrible mistake and I did not set the retract to be at the top of the stock, but at the top of the hole. I could have stopped it, but instead, somehow I just watched hypnotized and then paralyzed, when I could have pressed feed fold or e-stop. Fuck! Oh, I could really use a Ctrl Z right now. It's time to figure out if and how I can save this part. The tip of the drill almost went through. I was almost there. The best solution for this would be a die sinker EDM, but since I can't access one, my last chance is the TIG welder. I'm trying to build the metal stalagmite on top of that broken drill, then weld a knot on it. This method works well with broken bolts and I was even able to remove broken M4 screws. Please work, I have even the toe fingers crossed. But the drill was broken in more than one piece. There is no way I can remove the buried one without a die sinker EDM. So I'm left with this half success. There is a way I can still save this part. I could interchange the position of the hole so that the ball detent is placed where the locking pin is now and vice versa. But after the experience I just had, I figured out that when making the hole for the locking pin, at the intersection with the big hole, I would end up cutting with only half of the drill, so I might end up breaking another drill and completely ruin the part. So what I'm thinking is to temporarily plug this hole so that both flutes of the drill have something to grab on. I don't know what was in my mind when I thought I would use Loctite 638 to temporarily hold this pin, but this was my second big mistake in less than an hour interval. After I've messed up once, this time I made sure that my retracts are really retracts and now it went smoothly. Luckily the counterbore holes do not intersect with the messed up holes, so in theory I could still fix them. But I'm going further with some chamfers. Okay, it seems that we've got a new chance. Time to remove that plug. When I said the new chance, I meant a new chance to mess it up. Let's make a test. Pause the video now and guess what's going to happen. The stub is out, but I just realized that my obsession for tight holes, I mean tight fits, combined with Loctite 638 was an extremely bad idea. And now I'm just pushing it deeper. I guess my brain was offline. If I want to have a chance of pulling this out, I need a better grip on this pin. I just got what in the specialty literature they call Pinus Captivus. Let's try heating it up. The Loctite has a max temperature that it can withstand, which is about 180 degrees Celsius. If I pass the threshold, that should destroy the chemical bond. But as I said, my brain was offline, so I did not realize at that moment that heating the pin won't help. So what did I do? Try some convincing work with the oxypropane torch. Now it was so hot that I could barely touch it with the welding gloves, but still nothing. With all this heat, the pin has dilated even more, locking itself more firmly into the hole. But suddenly, my brain has started to intermittently respond on pings, so I had an idea. And for that idea, I need a center hole. I remember that I have a bearing extractor that I could use. I don't want to leave any dents now, so the copper shims are mandatory. I think the idea is good, but a bit difficult to put in practice with only 2 hands. What complicates the things even more is that the hole is not on the center, so the jaws of the extractor cannot grip uniformly. To prevent slipping, I had the brilliant idea of trying to use a glove to have more force of keeping the jaws tight. And then, disaster struck. The jaw slipped, leaving me with a quite deep dent.
Damn.
What should have been a trivial 20 minutes job of drilling and counterboring 2 holes has turned into 5 hours of discovering all the ways this could go wrong. You can't imagine how much frustration I had accumulated.
Incredibil, mă, incredibil.
Now when editing is kinda funny, but then I was mentally exhausted. It was already past 10 PM, but I had to step out a bit for a walk. Then an idea hit me on how to extract this pin. With these 2 V-blocks, I can create a larger contact surface to distribute the pulling force of the jaws. But it seems that even like this, the V-blocks are splitting apart. I hope that you guys watching would have had a better idea than this one. I realized just now while editing that the other end of the rod was free, so I could have used any stock of metal with a hole large enough for the rod to pass through. Then grab with the jaws of the puller from the back of that piece. But at that moment I was so mentally swamped that I could not see the simpler solutions. So I doubled down on the V-blocks. This C-clamp should hold them together while the extractor jaws are trying to split them apart when pulling. This is the sound of success.
Ura.
The chemical bond was now broken, and I needed a hell lot of a force to break it. I've learned the hard way how strong the Loctite 638 is, and that chasing tight holes is not always a good idea. In the end, as the classics say, not great, not terrible. At least now I have the holes that I need for the ball detent and for the locking pin. With the Pinus Captivus lesson learned, I took off a few hundred of a millimeters to make sure it doesn't happen again. Now, back to the mill, I can finally machine the last part of this assembly. And the dial indicator shows that we're ready to go. First, we'll do the milling for the I don't know how to call it feature. Nothing very spectacular here. Then, I need to machine a groove that will hold this locking pin in place. I could have done this on the lathe, but I wanted to constrain the range of movement to just 90 degrees. So I am plunging with a ball end mill. It should have been an end mill, but I was too lazy to change what I already had mounted. This operation and the following one were done in manual mode. Doing this in cam would have taken too much time for my current skill level. With the locking groove complete, now I need to machine the stable position of the ball detent. These are 1.3 mm deep, so they will take 1/3 of the 4 mm ball diameter. It's not quite done yet, but it has enough features to satisfy my curiosity. I already added the ball and the spring in place so that I can test how the ball detent would work. Also, this 4 mm drill shank will interlock with the slot I've just milled, so that I can temporarily lock it in place for the test. After tightening a bit the screw that puts tension on the spring, I can already feel the ball detent and it's exactly what I wanted. Let's test the mechanism. The mating part slides in and out easily, and when it's in the lock position, I have no play at all. Before I can take this off the mill, I need an 8 mm ring hole to mount the actuating lever. So, flat end mill, drill, and then a reamer. Off camera, on bandsaw, I cut off the excess length, so I can finally make it look nice. And finally, the less more complex part is complete. And after all the adventure, I'm quite pleased overall. And the last part that I need is the actuating lever. This needs an end threaded with M5 and this plastic ball that I knew I had it somewhere, and it took me just half an hour to find it. Off camera, in peace, with a fine file, I managed to hide the dents that I've made with the extractor. So now I can finally do the on-off engraving. After a weekend and many evenings, we finally have all the parts. The mounting order is straightforward. The first thing to mount is the cam pin. This will get locked in place by the end of an M5 screw turned down to a 4mm on its end portion. Now the movement of the pin is limited to just 90 degrees, but it doesn't have the stable positions yet. Adding the ball and the spring will do just that. These firm, stable positions and the clicking sound is what I wanted from the beginning. Now I can properly use the Loctite 638 to secure lock this lever in place. The cam pin integrates seamlessly, and the ball detent ensures that the locked and unlocked states are very well defined positions. In the end, I'm quite pleased on how it looks, so it's time for that long-awaited moment. After one last clearance check, it's time to mount the collet chuck. With these camlock spindles, you don't have to think twice if it's worth the effort of changing to a different chuck that's better suited for the job. The sliding door does not interfere with the lever, and overall, I think it does look like factory made. And by the way, the interesting thing about these chucks is that you can open and close them even while they're spinning. And if when I started working on this project my chucks were laying on the bench, in the meantime I found another unused spot that I could take advantage of. So this small trolley can store 3 of my chucks when not in use. And that's all folks. Hope you liked it. See you next time.